We will now solve the heat equation. Before we can solve it, we need to know what boundary conditions are. Boundary conditions are constraints that are applied to the edges of a domain in PDEs. They help with defining how a system will interact with its surroundings, making solutions unique and diverse. As an example, let's take a look at a rod with length L. Now, what I'm going to do is at the edges of the domain, namely x equals 0 and x equals L, I'm going to fix the temperature of the rod at its edges at 0 degrees. This is what is meant by a boundary condition. These set of boundary conditions are known as the Dirichlet boundary conditions. Another common type is when we have the same rod of length L and then we just make sure that no heat leaves the rod, so the edges at the rod prevent heat flux from flowing. This set of boundary conditions is known as the Newman boundary conditions. In this video, we will be learning how to solve the heat equation with these types of constraints: the Dirichlet boundary conditions and the Newman boundary conditions. We will now solve the one-dimensional heat equation with Dirichlet boundary conditions. So, recall that the PDE is partial u over partial t equals alpha partial squared u over partial x squared. To solve this PDE, we need to assume that u sub x of t will equal a function of space and a function of time. This will be x of x times t sub t. We do this so that we can separate it and simplify this PDE into two ordinary differential equations. Doing this, we should obtain the following: x of x times t prime of t equals alpha t sub t times x double prime of x. We now divide both sides by alpha times t sub t times x of x, and we'll get 1 over alpha t prime of t over t of t equals x double prime of x over x of x, and we need to set it equal to a constant, negative lambda. Doing this, we get two ODEs. For the first one, we get t prime of t equals negative alpha lambda t sub t. And for the second one, we get x double prime of x plus lambda sub x equals 0. We will solve the time equation, and if you know anything from ordinary differential equations, you will know that the solution to the temporal part of the equation will be t sub n of t equals e raised to the negative alpha times lambda sub n times t. The subscript n will be important later, but for now, we have solved for the temporal part of the equation. We have solved the temporal part of the heat equation, and now we just need to solve for the spatial part of the heat equation. So we have x double prime of x plus lambda x of x equals 0. The solution to this differential equation is just x of x equals a cosine square root lambda of x plus b sine square root lambda of x. Now we need to apply boundary conditions. And boundary conditions are essentially constraints, like what we have said earlier. We have our heat problem, and we have a temperature profile on the rod, use of x of t, and the endpoints of the rod, which is x equals 0 and x equals L, those are held at 0 degrees. So we need to apply this, and mathematically this is just x of 0 equals x of L equals 0. To apply this, we'll apply this boundary condition first, which states that when little x is equal to 0, x of little x is equal to 0. So we set that equal to this part over here. So we have a cosine square root lambda, and remember little x is equal to 0, so times 0 plus b sine square root lambda times 0. And we gotta evaluate this and simplify it. So the b sine part just goes to 0. Cosine of 0 just reduces to 1. So all we're left with is just 0 equals a times 1. And we know that a equals 0. So we've now reduced the spatial component of the heat equation into this. We're not done though yet. We still have to apply the second boundary condition, which is when little x is equal to L, x of x is equal to 0. And now we set that equal to this, so which is equal to b sine square root lambda of x. And notice when we gotta replace x with L, so that was a mistake on my part. So now, if you remember from pre-calculus, that sine will be equal to 0 for every n pi, for every integer pi. So we have square root lambda times L is equal to n pi, where n equals 1, 2, 3, etc. So we divide both sides by L, we get square root lambda equals n pi over L, and this is what square root lambda is, and similarly lambda will equal n pi over L squared. I just squared both sides to get that, so to get this, so yeah. And now the solution is, for the spatial part of the heat equation, will just be x of x, xn of x equals c sub n sine n pi x over L. I just changed it as c sub n because I like it better. So yeah, this is the spatial part for the heat equation solved. Now we solved the spatial part, and we also solved the temporal part of the heat equation. Now we just need to write out its full solution. So remember that use of x of t was equal to x of x times t sub t. Well, we can turn this into a linear combination, which would be use of x of t equals the infinite sum from n equal 1 to infinity of x of n of x times t sub n of t. So we replace x of n of x with this, and we replace t sub n of t with this. We just substitute that into this sum, and what we would get is use of x of t equals the sum from n equal 1 to infinity of c sub n sine of n pi x over L raised and e raised to the negative alpha. Okay, this is where this part becomes important, because from the temporal part of the equation, we had t sub t equals e raised to the negative alpha lambda sub n of t, right? So we could just replace lambda with this. So we have n pi over L squared times t, right? And this is actually the solution to the heat equation. So and this constant c sub n, well, we can actually just solve that using orthogonality like what we discussed last time. So if we apply our initial condition, u sub x of 0 equals f of x, we could see that c sub n equals the integral of L to 0, and we put this 2 over L here, of f of x, sine of n pi x over L dx. And that's how you would solve for c sub n. We've discussed that in the first video. So this is the general solution to the heat equation with Dirichlet boundary conditions. Let's take a look at the Newman boundary condition now.